Adding, subtracting, and multiplying complex numbers. What is a complex number? Let's think about all the types of numbers that you know. This could be the positives, the negatives, the rational and irrational, numbers like pi and all these numbers. All of those numbers fit into a set of numbers called the real numbers. Okay, every number so far that you know fits in this circle. And all of those real numbers are contained in a bigger circle of the complex numbers. What complex numbers are a combination of real and imaginary numbers. So this BI portion, this is an imaginary number. I is the imaginary unit. I is equal to the square root of -1. At this point, maybe you're seeing why this is imaginary. You cannot take the square root of a negative. All right, now, because I is the square root of -1, I squared is -1. And this is going to be super important later on. Adding complex numbers. To add, you simply combine the real with the real and the imaginary with the imaginary. So my real portions are this 5 and 3. So 5 plus 3 is 8. And then 2i plus -7i is -5i. So subtracting works the same way. But just like whenever we're adding and subtracting polynomials, we first want to distribute this negative and turn this into an addition problem. So as you can see here, changing the sign and distributing the negative makes this problem a lot easier. 2 plus -6 is -4. And -3i plus 18i is positive 15i. Here you go, you give it a try. All right, after switching the signs, 3 minus 4 is -1, and -2 minus 6 is -8i. To graph these, instead of an x and y axis, we have a real and imaginary axis. So if you wanted to graph something like 2 plus 3i, I would go out 2 in the positive real direction, 1, 2, and up 3 in the imaginary direction to give my point here at 2 plus 3i. Okay, so what would this point right here be? We didn't go either direction in the real, so it has no real component, and it went -3 in the I, so this is just -3i. All right, so let's give it a try with this graph. First thing I want to do is solve 6 minus 3i minus 4 plus I. So I switch my signs and change this to an addition. This comes out to 2 minus 4i. So on a graph, I go to the right 2 and down 4i to plot the point 2 minus 4i. Whenever you're multiplying complex numbers, they obey almost all the same properties as the real. We're just going to distribute this 4 to both of these terms to get 12 minus 4i. All right, now you give it a try on part B. Okay, and we should be looking at -8 minus 4i. Now, remember earlier whenever we said I squared is equal to -1? This is going to come back huge here in this next portion. If we distributed 2i to both of these terms, we would get 8i plus 6i squared. But remember, I squared is the same thing as -1, so we replace the I squared with a -1. Then I put it in the order a plus bi, so this would be -6 plus 8i. We can do the same thing multiplying two binomials by each other. We start by distributing the 2 and the -i to both of these terms. Distributing the 2 gave me 6 plus 4i, and distributing the -i gave me -3i minus 2i squared. Now I'm going to combine like terms and replace this I squared with a -1. That gives me 6 plus I minus 2 times -1. So my final answer, -2 times -1 is +2. So we have 8 plus I. Finally, let's talk about simplifying the powers of I. Like, what if I wanted to know, what is I to the 37th power equal to? The powers of I follow a pattern that repeats every 4 terms. I to the first is just I. I squared we saw was -1. I cubed is -I. And I to the 4th is +1. We saw earlier why I squared is -1. I cubed is simply I times I squared. So I times -1 is -I. And I to the 4th would just be I squared times I squared. And -1 times -1 is +1. And then this pattern just keeps repeating itself over and over and over. To simplify a power of I, just divide the power by 4 and look at the remainder. If the remainder is 1, it will be I. 2, -1. 3, -I. And 4, well, if it's divisible by 4, it won't have a remainder. Right? We can assume that this pattern continues in the other direction as well. Plus, so anything to the 0 power is just 1. All right, so let's try to use this pattern in this rule to find I to the 16th and I to the 9th. 16 divided by 4 is just 4 with no remainder. So because there's no remainder, I to the 16th must equal 1. 9 divided by 4 is 2 with a remainder of 1. Because 4 goes into 9 2 times and has 1 left over. Because the remainder is 1, I to the 9th simplifies to I. So I to the 37th, like we were talking about earlier, 37 divided by 4. 4 goes into 36, so it goes in 9 times and has a remainder of 1. So I know that I to the 37th is the same thing as I to the first power, or just I. And finally, what would I to the 39th be? 39 divided by 4. 4 goes into 39 9 times, but has a remainder of 3. So this is the same thing as I cubed, which was -I. All right, goodbye.